So welcome everybody to our second webinar in this series between CHEMRAWN, Beyond Benign and the International Younger Chemist Network. Good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining us. And thank you very much to Junji-san for agreeing to give this webinar with us. My name's Fran Curtin. I'm a professor of chemistry at Memorial University of Newfoundland in Canada, and I'm the chair of the CHEMRAWN committee for IUPAC. So IUPAC is the International Union of Pure and Applied Chemistry, and we work to unite the global chemistry community and advance chemical sciences through collaboration and free exchange of information. So CHEMRAWN stands for Chemical Research Applied to World Needs, and we're a standing committee of IUPAC, and we work on a range of projects and have people volunteering from around the world. This webinar is part of a project on promoting chemistry applied to world needs. We're also working on a chemistry entrepreneurship project led by the Committee on Chemical Industry, and with the International Younger Chemists Network, we're working on the global conversation on sustainability. A lot of our work ties in with the UN Sustainable Development Goals. IYCN, or the International Younger Chemists Network, is part of IUPAC now, and they have members around the world. If you're a younger chemist and would like to get involved, membership is free, and it's a good way to build your network of scientists around the world. So IUPAC and IYCN have been working on GCS Day, which is the Global Conversation on Sustainability. You can find out more about it on the website. It recognizes the day that the UN established the Sustainable Development Goals, and it's a way to share your research related to sustainability. Juliana Vidal is organizing a symposium at IUPAC 2025. And so we invite you to submit your abstracts to IUPAC 2025 and also for our special symposium. Beyond Benign, who are helping with this project and working with IUPAC, are an educational foundation focused on green chemistry and empowering educators to transform chemistry education for a more sustainable future. They organize webinars. There's the Green Chemistry Teaching and Learning Community Platform and the Green Chemistry Commitment. You can find out more through the links that will be appearing in the chat. So this project focuses on a webinar series, and we will also be preparing short videos for educational purposes for both high school students, university professors and students, and also the public. The webinars focus on UN's SDGs, particularly today's targets, a number of these, and also top 10 emerging technologies of IUPAC. The IUPAC Top 10 Emerging Technologies started in 2019, and every year 10 technologies are highlighted as being of importance and excitement around the world. You can read more about them in Chemistry International each year, but what we'd really love you to do is perhaps make a nomination for something that you would like to see recognized for 2025. Also, there is a special issue on so if you're a professor, perhaps you might want to contribute a mini review on one of these special emerging technologies. So now I'd just like to introduce our eminent speaker. Dr. Junji Nakamura is a research professor at the International Institute for Carbon Neutral Energy Research at Kyushu University. He received his doctoral degree from Hokkaido University in 1988. After postdoctoral work at Indiana University and the University of Washington in the USA, he joined the University of Tsukuba, I apologize for my pronunciation, as a lecturer in 1990 and was promoted to associate professor and professor in 2006. In 2022, he retired from that university and moved to Kyushu University, He has performed surface science studies combined with heterogeneous catalysis for over 40 years. Nakamura has extensively studied catalytic mechanism relating to methanol synthesis on copper-based catalysts, and one of his research papers published in Science in 2016 is the most cited paper with the keyword catalyst published in 2016. So welcome to Professor Nakamura. We look forward to learning from you.
Thank you for kind introduction, Frank. So, hi everyone. I'm Junji Nakamura. I'd like to start with this question. Do you think human emission of CO2 are causing climate change? The Cornell University group analyzed 88,000 peer-reviewed papers on climate change published between 2012 and 2020, and they report greater than 99% consensus of human-caused climate change. In other words, science says anthropogenic climate change is definitely true. Okay. Next, please. This is South Pole, and Antarctica is covered with thick ice sheet. The area of Antarctica is 1.4 times that of the USA. The average ice thickness is about 2,000 meters, and the 60 to 70% of the fresh water on Earth is Antarctic ice. So this is a striking phenomena, and this ice melting speed is little accelerated because the temperature of ocean is increased. So mechanism is the following. The high pressure beneath the large ice sheet is causing ice to flow into the ocean like a river. This is the glaciers. And the calving is a phenomena to make iceberg. Okay. So this is a frightening fact. Next, please. So let's look at the mechanism of greenhouse effect. The first, the sun radiates ultraviolet, visible light, and infrared rays. Then the Earth's surface is heated by this is called the black body radiation. Then the Earth radiates infrareds. Then greenhouse gas such as CO2, methane, H2O, and N2O absorb infrared. At the same time, greenhouse gas emit infrared radiation. So that's what, so that infrared rays travel back and forth in the atmosphere to heat both Earth and atmosphere. They finally dissipate into space. And the water or clouds are distributed unevenly above the Earth's surface. So that's why this looks like a greenhouse full of holes. But on the other hand, in the case of CO2, CO2 are distributed evenly above 10 kilometers from the Earth's surface. So that's why this is like a sealed greenhouse. So CO2 acts as a blanket to warm the earth. Next, please. No, the forward, please. Yeah. So let's look at the mechanism in more little detail. So first, solar is sun is very hot, 6,000 degrees centigrade. So that's why solar radiation have light with short wavelengths below 5 micrometer. So, and after heating the Earth, the Earth radiate light with long wavelengths above 5 micrometer. So the wavelength is determined by the temperature. This is the law of black body radiation. And the important point is infrared, okay? You see the maximum of the infrared radiation is located around 15 micrometer. Okay, so the CO2 molecule absorb the infrared ray with 15 micrometer. The mechanism is the following. The CO2 molecule is always vibrating, and the bending mode, bending vibration absorbs the infrared ray with 15 micrometer. This is the most important point for the greenhouse global warming. Okay, next, please. Yes. So let's look at the situation of global warming. And in the left figure shows CO2 concentration in atmosphere and the global temperature rise and emitted CO2 amount as a function of year. So the humanity start coal from 1850, followed by oil from 1950, then followed by natural gas from 1980. Then the emitted CO2 reaches to the 37 gigatons. In proportion, the temperature rise by 1.5 degrees centigrade, and the CO2 concentration rise to the 420 ppm. You see the good correlation, right? And if you look at the figure, middle figure, so you can explain that the emitted CO2 is from energy use, okay? So you see the global direct primary energy is increased, and emitted CO2 is also increased in proportional to the energy consumption. This can be explained by the equation at the bottom. And fossil fuel is composed of the carbon and hydrogen. And the CH species is reacted oxygen. This is the burning to get the energy, right? So 1 molar CO2 is emitted, and 800 kilojoule can be obtained. So that's why CO2 amount is proportional to the energy use. Okay, so if you continue to use fossil fuel, CO2 emission is continuing. Okay, so if you want to decrease the CO2 emission, you have to stop using fossil fuel and replace with renewable energy such as solar and wind power. So it's clear that the CO2 problem is equal to energy problem using fossil fuels. Next, please. And this is the definition of carbon neutrality. Carbon neutrality is a state of net zero CO2 emission, and this can be achieved by balancing emissions of CO2 with its removal or by eliminating emissions from society. And many countries have declared to achieve carbon neutrality by 2050 and 2060 for China. But you see the CO2 emission doesn't decrease. This is a serious problem, right? Next, please. So the question is where CO2 is emitted. So in the left-hand figure, the power plant emit most CO2. That's 40%. The next is industry sector, including steel, cement, chemical industry. So these two together account for 65% of all CO2 emission. But people tend to discuss the electric vehicle, something like that, but it's not the main issue, okay? You have to solve the CO2 emission from a power plant and industry, okay? Of course, recently the renewable energy is applied. For example, in the power plant, some solar cell are used, but the problem is after 5 p.m., supplying electricity in a way that responds to quickly to demand is very, very important. So sometimes in California, next to the power plant, battery is placed to supply the electricity in the night. But I think a battery cannot be used in anywhere, particularly in developing country. It's very difficult to use battery, okay? So I think it's hopeless, okay? So in that case, we have to make artificial fuel instead of fossil fuel, okay? So next, please. The promising artificial fuel is hydrogen. So anyway, the hydrogen is not the energy source, but energy carrier and energy storage. So, so you can get the energy from solar energy and wind energy. Then you can get the electricity, but it's difficult to convey and it's difficult to store. So that's why using electricity, you can make hydrogen by splitting water. Then hydrogen is transferred and stored. And finally, so hydrogen is converted to electricity by using fuel cell or internal engine. So this is a concept of hydrogen society. But next, please. But H2 is difficult to handle. And H2 carrier is necessary because the volumetric energy density of hydrogen is very small. If you carry the hydrogen by a tanker, you cannot bring big energy, okay, because energy density is so small. So the possible candidate of the hydrogen carrier is ammonia, methyl cyclohexane, and methanol. And you can see the table. The methanol and the ammonia are promising. These are promising energy hydrogen carrier. So next, please. And but introduction of artificial fuel is so slow. Why? Because fossil fuels are very cheap. Okay, natural system already prepared the fuel. The humanity just dig underground to get oil. It's like water. So think about it. The water price is comparable to the gasoline, right? Very, very cheap. But on the other hand, artificial fuels are very, very expensive because the production of artificial fuels require fuel for the manufacturing process. Okay, we have to know this point. Okay, if you want to solve the global warming, we have to pay money, big money. Otherwise, we cannot solve this problem. And then we have to discuss what kind of hydrogen carrier quantitatively using numbers. This is very important point. And the liquid hydrogen need the energy to cool down to minus 253 degrees centigrade. So advanced technology is very necessary, right? It's difficult. The ammonia, so for ammonia synthesis, it requires a high pressure of 100 to 300 atmosphere and 400 and 500 degrees centigrade. Also, you need electricity for this reaction condition. So, but on the other hand, methanol is relatively simple and mild condition of the reaction. So that pressure is about 30 to 50 atmosphere and the temperature is just 250 degrees centigrade. Next, please. But anyway, the point of the discussion of carbon neutrality is which artificial fuel to use. I would raise 3 candidates: liquid hydrogen, ammonia, and methanol. And in the case of liquid hydrogen, again, I think advanced technology is necessary for handling the liquid hydrogen. I think it's very difficult to carry out in the developing country. Anyways, climate change is a worldwide problem. So it's not only the rich countries' problem, okay? So everywhere, the new technology is necessary, right? So ammonia, also it's highly toxic. So, and its reaction process consumes a lot of energy. So I think the only option is methanol, because methanol is already implemented and existing technology can be used. So, and you can purchase the methanol at the drugstore. So everybody can handle the methanol, and it's good fuel, and it's good chemical raw material. All right, so next, please. And I'm writing the book entitled Proposal for Methanol Society. And this will be scheduled to publish this year or the next year. This book consists of 3 parts. Part 1 is as to what are the problems. Part 2 is as to the what path should we take. Part 3 is as to the what should we do, business, R&D, and policy, philosophy, and education. And the next, please. But methanol economy has been already proposed by Nobel Prize laureate Professor Oler and electrochemist of Professor Bockris. This is around 2005. But next, please. But actually, the methanol synthesis from CO2 has been widely studied since 1980s. I think the Japanese national project is the first to produce methanol from CO2. It's around 1993, and I was involved in this project. So I have studied mechanism of the catalysis for over 30 years. To be honest, at that time, I never thought the methanol would bring about the energy revolution. But after thinking about the energy efficiency and the carbon neutrality over recent 10 years, I believe methanol is the only energy carrier to solve the climate change, I think. Okay, because here you can make methanol easily. Just you can flow the CO2 and hydrogen through the black powder of a catalyst at 250 degrees centigrade. In any country, you can synthesize methanol. This is a good fuel. Okay. Also, you can recycle CO2. Okay. And after using burning methanol, you can also collect CO2. So you can establish a recycling system. Carbon element is very, very important. So you don't have, you never throw away the CO2. Okay. Okay, next, please. So this is the concept of a methanol society. Okay, methanol is produced from emitted CO2 from industry and hydrogen from renewable power, and the methanol is used for the chemical production and also energy. And after using methanol, CO2 is emitted. So you have to collect CO2. Then CO2 again is used for the methanol production. This is a recycling system. Okay. So the advantage is that you can immediately reduce CO2 emission. This is a realistic measure. Okay. And also the methanol has been already used as a fuel, and it's easy and safe to use. And basic technology is already established. So this is the methanol ship engine and the methanol car engine. And also you can use a fuel cell using methanol. It's not so dangerous compared to the ammonia. And also, methanol synthesis from CO2 has been already commercialized. This is the picture in China. Also, methanol can be used as a chemical raw material. In chemical industry, the main product is plastic, and the plastic is produced from ethylene and propylene, and the methanol can be converted to ethylene and propylene. So this is a big advantage. Okay, next, please. So the true innovation is cheap technology that can be used in developing countries or poor countries. So first of all, the methanol can be produced easily at the mild reaction condition, and the catalyst is cheap compared to the platinum and the palladium, iridium. You see the table figure. The copper is very, very cheap. And you can use the waste wood and the waste plastic as a reactant of methanol synthesis at the early stage. In the future, you have to use hydrogen from renewable energy, but at the starting point, you can use waste wood and waste plastic. And at the initial stage, you can use engine, okay? The technology has been already established. In the future, you have to use fuel cell. Okay, next, please. And methanol production plant has been already established, but the progress is slow. In Iceland, the company produced methanol from CO2 collected from air. And in Canada, CO2 capture at the power plant has been already operated. And in the right-hand side, the methanol synthesis plant has been established in Iceland, Germany, Sweden, China, USA, and Saudi Arabia. This has been already slow, begun, but it's slow. Next, please. The point is the business, okay? People don't move without money. So the business is very, very important, and the supply chain is important. So the political measure is also important. So there are three types of the hydrogen: green hydrogen, and blue hydrogen, and gray hydrogen. So ideally, you have to use green hydrogen, which is produced from renewable energy. But the blue hydrogen is produced from natural gas with capturing CO2. So maybe we can start from blue hydrogen, or even gray hydrogen. Gray hydrogen is without CO2 capturing. But it's okay if you can start the methanol business, okay? So the also CO capturing business and utilization of methanol utilization business is important. And the hydrogen price is very high. 70% of cost of methanol is green hydrogen. So that's why at the initial stage, you can use a cheap hydrogen from biomass or from natural gas. And expanding international market is important. And expanding methanol market is important. But the political measure is most important to promote methanol industry. Next, please. Also, the public awareness is important. In France, the French government established a convention of citizen participation regarding climate change in 2019, and 550 citizens were randomly selected, and they discussed climate change and measures for a half a year. And then they proposed recommendation, and many of them were adopted by French government. This movement changed the lifestyle of French people. I respect this movement. Okay, so this kind of citizen activity is very, very important. Also, making small, smart cities is important. So in Denmark, the small city, it's a kind of model city started. And they use the renewable energy and this systematic energy controlling system. So this kind of activity is necessary. Also, the philosophy is important. The mottainai spirit, which is the traditional Japanese value of not wasting things and recognizing the importance of things. This can be applied to energy problem. Okay, so we need to quantitatively discuss the energy efficiency of synthesizing new fuel and the efficiency of using electricity and heat. Suppose, what do you think about the one people with 70 kilogram drive the car of 1,500 kilogram? I think it's a waste of energy. Okay, after recognize the energy consumption, recently I try to take train or buses without driving a car by myself. So anyway, this kind of philosophy is necessary. Okay. Next, please. So let me summarize my talk. The urgency of climate change demands immediate action. CO2 emissions stem from fossil fuel combustion. Artificial fuels must replace fossil fuel, with methanol being the most viable option. A robust methanol supply chain must be developed. Public awareness and political action are essential. Next, please. So we must guard our Earth, so let's work together to tackle this global challenge. Thank you for listening.
Awesome. Thank you so much, Dr. Nakamura, for your presentation. I really liked the part where you said about true innovation is cheap technology that can be used in developing
Yes.
countries. So thank you so much for that. We
Yeah.
have some time for questions. We have some questions coming up in the chat. So one of the questions that appeared was regarding the energy storage. So they said that the energy storage is relatively higher in artificial liquid fuels. Is it better than artificial liquid fuel? So that's the question. You can see the question in the chat too.
The question is, liquid fuel is important. Yeah. When it comes to the energy density, the liquid is very good. The solid is not so good, okay? Because ignition is slow, okay? And distinguish fire is slow, right? So you can vaporize liquid fuels. So And so that's why the liquid fuel is ideal material. Okay, so it's easy to bring and easy to store. Okay, but electricity is not so good. So in the case of liquid fuel, you can bring the fuel everywhere by truck or car or something like that. But if you use electricity, you have to make a line, right? Electric line, right? Everywhere. So I think anyway, we have to solve the problems as early as possible in anywhere. So in that case, only choice is liquid fuel, I think. Yeah.
Awesome. Thank you so much,
Liquid
Junji.
hydrogen is, yeah, liquid hydrogen is too expensive. Okay. And ammonia is very, very dangerous. And incident always happen. So if the small concentration of ammonia is very, very dangerous. Okay.
Awesome. Thank you so much. We have another one that's very deep. So, how optimistic do you feel about achieving net zero by 2050 or even by 2060?
Anyway, so this is a great question, and it's very, very difficult. Okay. Very, very difficult. So, and the point is, company and government don't move without money. Okay, they fear the public or citizen. Okay, because they cannot. The business is important. The reputation by citizen is very, very important. So I think only hope is SNS, okay, public awareness. So that's why we have to act. The academia are responsible to publicize this important information. So that's why our CHEMRAWN are responsible for this matter. Okay. So this is a kind of chemistry. Okay, you have to make artificial fuel, so that by chemical reaction. So the chemists are responsible for this very important task. So anyway, so we have to publicize to the public using SNS like this. Okay. So that's why I just start. Maybe I will talk in the TED talk or something like that. Anyway, so I will apply this year. Okay. All right.
That's awesome, Junji.
But anyway, so very difficult anyway. Okay. I'm not so optimistic. Okay.
Awesome. Thank you for your honest response. And you mentioned a lot about the public awareness of how we need to get out there and talk about the problem and also show how we can solve it. So in terms of the public, are any other actions that are very effective that you think we should be talking to them, like do this, do that? And if you think there are any actions that we should be telling the public to do, which ones are the ones you think we should be doing so?
Yeah, great question. So like French, okay, maybe I think we have to establish a citizen conference in any countries. Okay, discussion activate the motivation. Okay, so that's why the acting. Well, you can use a bicycle or something like that. Okay, and you can say something, and also the anyways, as I mentioned, I respect the French style. Okay, so I know that in Germany and in England, the similar citizen conference has been established. But this kind of particularly in the big country, okay? So like United States and in China, maybe the citizen movement may be very important, I think, yeah. That's my opinion, yeah.
Awesome, Junji. Thank you so much. I don't think we have any more questions, but we really appreciate not only your time for being here talking to us, but only like bringing this problem, bringing the solutions, and something not only us as academics and scientists, but as people, we should be doing and talking to other people to solve it. So I really appreciate your time.
Yeah.
I
Thank
just
you.
have some closing slides here that I'd like to share with everyone. So I hopefully will be able to see my screen soon. Just a second. Technology, please help me here today. Okay, so I hope you can see my screen. Yeah, so thank you, Junji, again for your time, your presentation. It was lovely. Also, I'd like to just call out again here if you wanna like nominate any technology for the IUPAC Top 10 Emerging Technologies, please do so. You have the link here. And also, if you want to contribute to the Pure and Applied Chemistry special series on these emerging technologies and show out there your work related to these, please do so as well. I'd like to talk to you about some of Beyond Benign events that we're hosting. So at the end of the month, we'll be having a green chemistry commitment info session. So if you're interested in bringing green chemistry to your department and how you do so, please, you can read the QR code. And also we have some link in the chat. Hopefully I cannot see the chat, but so you can join us at the end of the month. And also just continue the conversation. We have a platform around green chemistry that's open to everyone to participate. It's called the Green Chemistry Teaching and Learning Community, and it's a place for us to continue this conversation and promote more sustainable actions to our society. Also, we have some events called Green Chemistry Connections. They're held monthly. The next one, I think it's happening on February 18th, if I'm wrong. Chloe, just jump in. 19th, sorry, 19th. And we'll be talking about green chemistry outreach and some opportunities there. So lots of opportunities to talk about green chemistry. And also, if you are a teacher or knows a K-12 teacher, we also have a series dedicated to green chemistry education in the K-12 space. So we really want you to join us, and we'll be in touch whenever we have more information about our next event in the series. You'll be receiving an email from us. Thank you all for enjoying your evening, afternoon, morning with us. Thank you so much, Junji, again. Thank you, Fran. Thank you, Chloe. Thanks all of you. So we hope to see you all again.